Okay, so quick review of where we left off yesterday. We talked about component form of vectors and magnitudes. And remember, there's different ways to write this component form. X component, Y component, X, Y, a third one for Z, or I guess let's do the one down here. X times I hat plus Y times J hat plus Z times K hat. It's the three-dimensional one. X, Y, Z. Generally don't prefer the hat notation, but that's what's common in physics. But it's important to know it, and once in a while it is more useful, and I'll end up showing you that when we do the cross product. And the magnitude is just the Pythagorean theorem or the three-dimensional version, which is square root of x squared plus y squared plus z squared. Um, this is how it shows up in the um, IB formula booklet. Useful to know. You will definitely need that. Um, and keep in mind that important pieces of information are going to be given a lot of times in these vector formats. 30 means 30 and the x. As far as the meaning, it means 30 this way. So think on a graph, 30 and then 40. And my actual vector is the hypotenuse. So a ship is traveling from port A, travels with velocity 30, 40 kilometers per hour. How far will the ship be from port after 10 hours? Well, I can go ahead and find the magnitude here. So that's 50. So it's 50 kilometers per hour for 10 hours. 50 times 10 is 500 kilometers. What are the coordinates? Well, I can just take it in component form. It should be written in coordinate form. So 30 each hour for 10 hours, 30 times 10, and then 40 up for each hour gives me 300, 400 is my location. And that's our component form. International mindedness. There's a global decline in the number of bees. Bees are important for pollinating. Without them, many food crops would not grow. Around the globe, wildflower gardens are being built in cities to provide suitable habitats for bees to survive and try to halt the decline. Um, so this is, a thing about bees worth watching. Also is going to apply vectors. So potential application of vectors with bees. Unit vectors is going to be our last thing in this introduction to vectors thing. And a unit vector is a vector of magnitude 1. Okay. This particular vector we have here is a vector, and they show its magnitude 5. Its unit vector, we'll call it vector W. You just take each component and you divide it by the magnitude. 0 divided by square root of 5 is just 0. So they're denoting unit vectors. Oh, okay. I see how they're notating that. They're calling it v hat. Actually, that looks kind of like a rounded hat instead of a triangular hat that we usually use in I hat, J hat. The unit vector, one of the keys. Oh no, they are using a triangular hat here. Okay, phi hat. One of the keys. So yeah, that actually makes some sense. I hat being a unit vector of one in the horizontal, j hat being a unit vector of one in the vertical. That's horizontal, that's vertical. K hat being in the in-out direction, unit vector of one. So those are all unit vectors. The hats, I guess, mean unit vector. I never knew that. And they show it here. I'm not sure if this is in your formula packet, but you're just dividing by magnitude. Remember that vertical lines means magnitude of the vector. So find the unit vector for W. First thing I need to find is magnitude of W. And that's square root of 2 squared plus 3 squared plus 6 squared. 36 plus 9 is, oh, that's 7. That's such a nice number. Wasn't expecting that. So that's 45 plus 4 is 49. Square root of 49 is 7. And so my unit vector, I prefer them distributed through. So I just take each one 10/7. So that's example one. So this one gives me 2 points, and it's going to eventually ask me to find a unit vector in the direction of AB. So first thing, vector AB is going to be from 1 to -4 goes, that's -5. From -3 to 0 goes 3. So the key is the vector does go from A to B. And it's what am I adding to these? From 2 to 3 is 1. What am I adding to the points from A to get to B? The distance between them is the magnitude of the vector. That's square root of 35. My unit vector, again, take each one, divide it by the magnitude. Or if you want, I suppose you could just do this. And I do prefer this matrix notation. It's going to get real useful later on. Yeah, they gave it in factored out form. So looking at another one, consider the points A1K, A1K2, B4, -2, 1. The length of the vector is square root of 46, and find K, and then the unit vector in the direction of AB. So AB, let's just do it in this form. From 1 to 4 is 3. No, I did that backwards. 2, -1. So from 2 to go to 1, I want -1, which means I'm going 1 minus 2. So I am having to go backwards and thinking about this. So I know that the square root of 46 equals the square root of 3 squared plus -2 minus k squared plus 1 squared. And yes, I'm dropping the negatives because when I square them, they become positive. I don't even have to think about it. So those are 10. I'm going to subtract. This is 36. I don't really need the minus. Oh, actually, I guess I do. I add 2 and I get 6, or -4 equals -k. So k equals -6, or no, not 6. When I add 2 to both sides, I have to add it separately to each case, the +2 and the -2. So it might be best to think of this as 6 equals -2 minus k and solve that, and -6 equals -2 minus k. This one, when I add 2, I get -4. 4 is equal to k. When I add 2 to this one, I get 8, -k. So k, that's a liter, is -8. So those are my options. So my vector AB is going to either be 3, well, this -2 minus k, I guess, is 6 or -6. I guess I didn't really have to solve for that. I didn't really have to solve for k. So my unit vector is either this or and again, you could distribute it, but one of those two options. And yes, they do show it as both. They are notating the unit vector like this. AB with a hat over it instead of the vector arrow. It is very important, and I'm going to emphasize this again, that when you handwrite them, you draw the vector arrow. Sometimes they will give vectors by just bolding the letter. You can't handwrite bold, so you have to draw the arrow. Don't assume they know it's a vector. Okay, scaling. When you multiply a vector by a scale factor, you create a new parallel vector to the original one. And they emphasize parallel. Yes, they're in the same direction. But you can say parallel because vectors have no position, so you could just slide them around. Okay? But if vectors are always parallel to each other, if you need to find a vector in the same direction as a given vector, but a different magnitude, you can find a unit vector in the required direction and multiply it by a suitable scalar factor. Find a vector 2 units long in the direction of 1, 1, 1. So first thing I'm going to do is find the unit vector. Square root of 1 plus 1 plus 1 is square root of 3 is the magnitude. So my unit vector is 1 over square root of 3 1 over square root of 3, 1 over square root of 3. It has a length of 1. So if I wanted to have 2, I just multiply by the scalar 2. So I'm going to call this directed vector x. So x hat is this. In that direction, I'm just looking for 2x hat, which is then 2 over square root of 3. Or probably in simplest form, factor it out. I think I like my factored out version slightly better. But either way, all of them are the same. And that is the end of Introduction to Vectors.